So here we've got an exponential model representing the number of newts in a lake, where n is the number of newts and t is the number of years. So t is our time in years. A and b are just constants which we need to find. So I've got that represented here. Now here there's a linear representation of the number of newts. So, but here it's got log of n on this side and then t in years here. And that's what it looks like in a sort of a straight line. This is going to create some kind of exponential curve in that kind of pattern, something like that. And what we want to do is complete the exponential model. So we need to find these constants a and b. And we need to find out when the number of newts will be multiplied by 10 from its initial amount at the beginning of this investigation, shall we call it. So what we're going to do first, we're going to try and make some sort of sense of this. Now we can see here, we can work out a gradient of that because that's just a straight line. So what I'm going to do first of all, I'm going to take the logarithm of both sides to get log of n. And then that way then we can make some sort of sense of what's going on in here. So if I take the logarithm of both sides, I'll have the natural logarithm of n and then the logarithm of this side. So I'll go a, b to the t, put it all in a bracket. Now a and b here, these are multiplied, a times b to the power of t. Now what I can do is, if I've got the log of x, y, that's the same as the log of x plus the log of y. So that's a logarithm rule we can use here. So let's apply that to the right hand side. So then I've got the log of a plus the log of b to the t. Okay, now that's good, we've got that separated. And then now we've got this log of b to the power of t. We want to get something that looks a bit like y equals mx plus c. So here we've got m multiplied by x, here we've got something to the power of. So we need to apply another logarithm rule. So if I've got this one here as another example, ln of x to the power of y, that's equivalent to y ln x. So I can apply that to this one. So let's apply that rule here. And now I've got natural log of n. Now this log of a, that could be my c value. So I'm going to put that to the right hand side. So I'm going to put that there, keep my plus sign. And then here when I've got x to the y, I can just bring my t to the front and multiply by ln b. So t ln b. Okay, so that's what I've got. Now what I can do is I can apply that here, find my gradient, and then work out which one of these is our gradient. So let's find the gradient here first of all. So changing y over changing x. So what have I got? Changing y goes from 4.2 to 3. And changing x goes from 5 to 1. So 4.2 minus 3 is 1.2. Actually, let's do it down here so we don't interrupt on this side. So we've got 1.2 over 4. So in decimal terms, that's just going to be 0.3. So that's 0.3. So that would represent my gradient. Now, which is going to be the gradient after t or ln of b? Well, I've got t here, that's a variable. So therefore my gradient must be natural log of b. So natural log of b, that's going to be my gradient. So we can put that in here for now. ln of n equals ln of b, that's 0.3. So I've got 0.3 t plus ln of a. Okay, now looking at the exponential model, y equals mx plus c, if I want to find my gradient here, I can get b isolated, that will represent my m value, so I can exponentiate both sides. So if I do e to this and e to this, I then can solve for b. And then b will come to approximately 1.35, give it to 2 decimal places on our calculator. So we've got the b value. Now we need to work out what our a value is. Now here on our graph, this is assumed to be around about 2.7. So here ln of n equals 2.7 at t equals 0. Okay, so at t equals 0, n is 14.8. So let's work out what we can do with that. So let's just draw a little line here. So 14.88, that equals a times b to the power of t. Now a we don't know yet. B, do we know what b is? That's 1.35. And then to the power of t. Well, t we know is 0, so we can change that to a 0. So 1.35 to the power of 0, that's just 1. So if we're multiplying a by 1, then a must be 14.88. So a equals 14.88. We've got b equals 1.35. So that completes that. So now what we can do is we can work out our answer to this question. When will the initial number of newts increase by a factor of 10? Now we can just be a little bit careful here. We've got our initial amount of newts as 14.88 here when the beginning. Now we can't have 14.88 newts, so I'm going to use 15. So here, use 15 for that reason. So I'm going to use that in my model. So we've got n equals a, which we're going to use 15, times b. b is 1.35 to the power of t. Now we want to know when the initial number will increase by a factor of 10 here. So we need to multiply by 10. So here our initial amount is 15, so we want to know when it's 150. So 15 times 1.35 to the t. Divide both sides by 15. So this is the bit where we can see that when we're trying to work this out, it wouldn't have mattered if we'd have put the 14.8 in here either, because when we would have had 148.8 and then divided by 10, we still would have ended up with 10. So hopefully that's okay for you. So now we're going to do solve for t. Now, for solve for t, what I'll do is take the logarithm on both sides. So I've now got ln of 10 equals t times ln 1.35. And then all I do now is just divide both sides by 1.35. So divide that by ln of 1.35. And that equals t. That will disappear. And if you put that in your calculator, you get approximately just under 7.7. So t would be approximately 7.7. So that means this will happen in approximately the 8th year. So we're looking here, the 8th year. So the 8th year, the number of newts will increase by a factor of 10. The exponential model, we can now complete that. Let's just write that next to it. So n equals, we're going to use 14.8 for accuracy, times 1.35 to the t. And that's our exponential model completed as well.